Okay, this section is on arcs and chords, so it's titled Arcs and Chords, and really it's just introducing more vocabulary. We're still in the stage of, before we start working with circles, we're going to continue to introduce some new ideas about different ways to look at circles. Okay, and so I want you to kind of try and think with a blank slate about circles, and we're going to start here in this section introducing some new ideas to you. So that's the center. So you heard one of the descriptions we used in class the other day was that one way to define a circle is that it has 360 degrees. Here's what that means, is that if I go all the way around the circle, I'm covering 360 degrees worth of rotation, right? So we've talked about how a line, if I were to draw a line or a diameter, so I'm going to draw like a secant through the circle. So from here to here would be a diameter, but this technically would be a secant since it goes through the circle. That this part of the circle measures 180 degrees, and this part of the circle also measures 180 degrees. So in full, the circle measures 360 degrees. So when we talk about parts of the circle, when we talk about different parts of the circle or sections of a circle, instead of using the whole, we talk about it in degree measures. Here's what I mean. Let's say I were to draw an angle from the center of this circle. So an angle that looked like this. Let's say I tried to draw a right angle. So I'm actually going to redraw that so it looks a little bit more like a right angle. So this would go straight here, and this would go straight here, and I'd make this right. First of all, this is a special type of angle called a central angle. And I'm going to write that down. A central angle. An angle that comes from the center of a circle is called a central angle. So if this angle measures 90 degrees, then this section of the circle right here is called an arc. Okay, that's called an arc. A-R-C. It's only a section of the circle. It's not the entire circle. It's a specific section of this circle that measures a certain portion. And we refer to arcs. Arcs have both a length, an actual length, and they have a measure. They have both. And we talk about the measure of the arc. And the measure of an arc is the same as the measure of this angle. So for example, since this angle in the center, this central angle is 90 degrees, we would also say that the measure of this arc is also 90 degrees. So since this angle measures 90 degrees, it would make sense that this arc measures 90 degrees of the circle's 360. If the circle measures 360 degrees all the way around, then this part of the arc measures 90 degrees. I want you also to recognize that that's different than a length. A length of this circle would be part of the circumference. The length would be, who knows, depends on how big the circle is, but maybe let's just say it's 2 feet. Those are both ways to measure arcs. We can talk about both the length of an arc and the measure of the arc. Okay, and those are two separate things, but they're both ways to account for arcs, to measure arcs. Okay, so if this is a central angle, what I'm going to do is I'm going to make a list over here of kind of the terms and the things that you need to understand. I'm going to describe a definition to you, but really what I want you to see is I want you to have a picture of all of these things in your head. Okay, so if you need to pause the video at any point and kind of draw this picture, add this picture to your sheet of pictures that you're allowed to have, then feel free to do that. But this list that I'm making over here will kind of be the comprehensive list of all of the things that you need to be able to use in language and understand from this chapter. Okay, so if this is how we measure arcs, then we can have different types of arcs. For example, I'm going to erase this. One of the types of arcs that we can have is something called, I'm going to write it in blue, a minor arc. Okay? And a minor arc is any arc that measures less than 180 degrees. So I'm going to draw it in blue on here. So if I were to draw a diameter, I'm going to draw a diameter in green right here. I'm going to do my best to draw. That's good enough. If I were to draw a diameter in green, this equals 180 degrees. So if I were to draw a central angle here that measures less than 180 degrees, clearly that measures less than 180 degrees, then this, since it measures less than 180 degrees, since our angle is less than 180 degrees, this is what we would call a minor arc. Now, I'm sure you're guessing, just like there are minor arcs, there are also things called major arcs. Major arcs, okay? And a major arc, as I'm sure you're guessing, is greater than 180 degrees. Greater than 180 degrees. Okay? So if I were to draw an angle like, let's say, here's one, just like this. What if I'm referring to this angle right here, that's greater than 180 degrees. So this arc in red corresponds to that angle. And so whatever the measure of that angle is, the measure of this arc, but clearly it's at least above 180 degrees, so we would call this, that's in red, a major arc. Okay? That's a major arc. If an arc is if a line or an angle drawn through the circle is a diameter, so if it's a straight line across, if it's a diameter, then we have a special name for exactly half of the circle, and you've heard this before. That is called a semicircle. An arc that measures exactly half is called a semicircle. Okay? And then the last thing that we need to talk about is congruent arcs. Okay? Congruent arcs, and I'm going to write it here. Congruent arcs are any two arcs that have the same measure. Congruent arcs are any two arcs that have the same measure, meaning their central angles are the same. Okay? So, central angles, you need to know. Minor arcs, arcs that are less than 180 degrees, you need to know. Major arcs, you need to know. Semicircles, you need to know. And congruent arcs. Those are all things from this slide that you need to have a conceptual understanding of. The last thing that I need you to remember that we talked about was this idea that there are two ways to measure arcs, and that's both a length and an angle. Whatever the measure of the central angle is, that will also be the measure of the arc. I really need you to, whatever you need to do, to hammer that home. Okay? So we're going to do a practice problem together, and I'm going to talk a little bit about the way that we notate and we talk about arcs. Okay? So moving on to the next slide, here's what we have. We have MP, that is a diameter. Okay, so it's telling us that MP is a diameter. I want to talk about first how we notate some arcs. So there's lots of arcs in this picture. Okay, I'm just going to start talking about one of them. One of them is this distance right here. How we refer, that clearly is an arc. The measure of that arc will be the same as the measure of its angle. So its central angle is 80 degrees. So the measure of this arc would be 80 degrees. The way that we refer to this arc in notation is like this. That is arc MN, and we draw a little curved line above it. That's how we refer to arc MN. If we want to talk about the measure of an arc, just like we talk about the measure of an angle A, we would talk about the measure of an arc by writing a little m in front of it. The measure of an arc equals this. If I want to talk about the length of an arc, then I just write this. If I see this, it's saying the length of the arc MN is this. Now, in general, you need to understand that this little m means measure, so if it says little m, then it's asking for the measure. Okay? So what I want you to do now is I actually want you to pause the video, and I want you to list as many arcs as you see in this picture. List them here. So one that we've already done is arc MN. I want you to pause and make a full, as comprehensive of a list of all the arcs that you see here. And when you're done, replay the video. Okay, so hopefully you have a list of arcs. And I want to take you through how many arcs are in here. We're going to try and get them all, but I might miss one. We'll see. So another one that I can clearly see is this arc NP. So NP is an arc. Okay. This is an arc. It's a semicircle. That's arc MP. Okay, I'm going to start erasing this because I want to show you. Okay. I also can go all the way from M all the way around to N. That is an arc. So that would be the arc. Be careful now, because if I just say I'm going from M to N, so if I just go arc MN, well, I already had that one listed, and we're referring to this. So when you're listing arcs, you have to list all of the points in between. So this arc here wouldn't be arc MN, even though we are going from M to N. That arc there, we would actually call it arc MPN. And that would be the way that we would make sure that we know we're going this direction through P first before we get to N. Okay? And so arc MPN would be the same as arc NPM. Okay? All right, let me see here. Let me see if I can see any other. Okay, just in the same way that we had MPN, PMN is very clearly, or NMP. Is that the same as arc MPN? No, it is not. And once again, we see here why the notation matters so much. If I go from N to M to P, that's going to be a different measure than the other arc. So arc MNP would be another arc that we could list. And there might be more that we can list here, but for now, that's going to be a good list of all the arcs that we can see. And what I want you to do now is I want you to go through and I want you to try and list the measure of each of these arcs. Remember, the measure of the arc is going to be the same as the central angle. So all you need to do is find the central angle, knowing that a full circle is 360, and whatever that central angle will be the measure of the arc. So take some time. We already did MN. We already said that the measure of arc MN was 80 degrees. And we already know that MP is the diameter. So take some time and try to fill out what each of the measures of these arcs are. So pause the video and do that now. Okay, so hopefully you have an answer to each of these questions. Let's just keep going here. Arc MPMN. Sorry, the measure of arc PMN. So we're going from P to M to N. Well, if we know that MP is the diameter, then we know the measure of this arc right here is exactly 180 degrees. So to find PMN, we need to take 180 degrees and add it to 80 degrees. So 180 plus 80 is 260, and that's going to be the measure of arc PMN. Okay, but now what about arc MPN, going from here to here to here? In order to do that, we need to know what the measure of this angle is right here so we can find the measure of this arc right here. How can we do that? Well, once again, we're going to use the fact that MP is a diameter to help us. If we know that MP is a diameter, then we know for certain that together this right here is going to be 180. If this is 180, if this is 80, then this is going to be 100 so that that diameter can measure 180. So let's talk about this again. So MP is 180, PN is 100, so 180 plus 100 equals 280. And then we already talked about right here what the measure of arc PN is. Arc PN is 100 degrees. Okay, so that's how we use the central angle to determine the measure of each arcs. What we're going to do now is we're going to go through several postulates and theorems that you need to know, and then you can do the practice problems that are on your PowerSchool page for Chapter 10, Section 2. First is the arc addition postulate. The measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. Here's what this is saying. Let's say we have a center here, and so we have an angle that goes from here to here, and then an angle that goes from here to here. We have two angles that are touching, making two adjacent arcs. That's what an adjacent arc is. One is AB, and the other is, I'll do a different color, is BC. What this theorem is saying is that the measure of arc ABC, that whole arc, is the measure of arc AB plus the measure of arc BC. So if I have two adjacent arcs, I can add them together since they're adjacent, and I will get the measure of this bigger arc. That is why it's a postulate. Remember, postulates are the rules that we can just generally accept to be true. They don't really need to be proved. Let's move on to Theorem 10.4. Theorem 10.4 says, in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Okay, this one's a little bit different. Let's draw a picture to really hammer home what we mean. Let's say I have one chord right here that is chord AB, and I have another one here called chord C, D. Okay, so I have two chords. And let's say these chords are congruent. So I have these congruency symbols right here. Well, because these chords are congruent, you can see that an arc is created by these chords. Here's one arc. We would call that arc AB. And here's another arc over here. We could call that arc CD. And what this theorem says is that if these two chords are congruent, then we can say for certain that these chords that are created by these arcs are going to be congruent as well. So in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Okay? And we can use congruency symbols to talk about that, but I would just write it this way. AB, arc AB is congruent to arc CD. Okay? Pretty straightforward. Let's keep going. We got three more theorems. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Here's what it's saying. Let's draw a diameter as best we can. If a diameter of a circle, here's our diameter, is perpendicular to a chord. So I'm going to draw a chord. I could draw it anywhere, but I'm going to draw it right here. That is perpendicular to this diameter. Okay, so it measures 90 degrees. Then we know that the diameter bisects the chord and it bisects its arc. So here's what this is saying. That if these two are perpendicular, then here's the chord. It bisects this chord. It cuts it in half. So this section of the chord is going to be congruent to that section of the chord. Well, you can also see that that creates an arc. There's an arc, and there's an arc. And if a diameter bisects a chord, it not only says that these two sections of the chord are congruent. What we also know is that this arc and this arc is congruent to each other. Okay, so let's add some notation so that we can write out these formal rules. So let's say this chord is going to be AB, this chord is going to be CD, this diameter is going to be CD, and they're going to meet at point M. Then what we would say is if the diameter of a circle, so if in our picture AB is perpendicular to CD, and in this case, CD is a diameter, then both of the following things are true. Then AM is congruent to MB. Those are the segments. This is congruent to this. And arc AC is congruent to arc CB. Both of those things are true when we have a diameter bisecting a chord. All right? So, moving along. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Okay, so Theorem 10.6 is actually the converse of this. So we're not going to go into as much detail about this one, but let's say I have a chord and another chord, and one of these chords is perpendicular to and it bisects the other chord, then we know for certain that this first chord, guess what, has to be a diameter. Has to be a diameter. So this is the exact converse of this. This one says if a diameter is perpendicular to a chord, then we know that it bisects the chord and its arcs. This one says if one chord is perpendicular and bisects another chord, then we know the first chord is a diameter. So it's really the converse. If you understand 10.5, you don't really need to have a full grasp of 10.6 because they're really the same thing. All right, moving along to our last theorem in chapter 10, section 2. In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center of the circle. I'm going to use our same picture as before. Here's the picture. Two chords. Okay, I'm going to try and draw them relatively the same. Those are close enough. One AB and one CD. Here's what this is saying. If these chords are equidistant from the center, if I were to draw a straight line from this chord to that chord, and to the center and the center to this chord, if these distances are the same, then we know for certain that AB is congruent to CD. Okay? That these two chords are congruent if they are equidistant from the center. So if we go back to theorem 10.4, if these two chords are congruent, that also means that we know that they are also equidistant from the center. That this distance and this distance must be the same. Okay, so it works both ways. If chords are congruent, their arcs are going to be congruent, which is what theorem 10.4 says, and we know they're going to be equidistant from the center. So there's lots that we already know just from chords being congruent. We know these arcs are going to be congruent and that this distance here is going to be congruent. Okay, that's chapter 10, section 2. I know that was a long section. I appreciate your level of attention. The practice problems are listed on the PowerSchool page. You can go ahead and do those now. Thank you.